All right, guys. So in this final video for Unit 6 and 6.7, we're going to be talking about a number of things. We're going to kind of bring everything together that we've been talking about so far. We're going to talk about classifying polygons. So we're going to talk about the different names that we have for them. We're going to talk about regular polygons as well as the area for regular polygons. So these are going to be some kind of special types that we're going to look at. But first, let's just talk about how we classify polygons. So polygons are named by the number of sides that they have. If it has 3 sides, that's pretty easy. We're pretty familiar with triangles. 4 sides is a quadrilateral. Now there's a lot of different ones with 4 sides, so it's easy to want to say a square, rectangle, parallelogram, all that kind of stuff. But really for 4 sides, it should be a quadrilateral. For 5 sides, that's one that you probably remember pretty well, is pentagon. And then there's some other ones like 8 sides and octagon that you'll probably remember pretty easily. But there's some other ones that are a little bit harder to remember. For instance, 6 and 7 sides have very similar names. 6 is hexagon, 7 is heptagon. The way I've always remembered to keep those separate, 6 sides, the word 6 has an X at the end of it. And so that's the one I know it has to be a hexagon because hexagon also has the letter X in it. So that's just the way I've remembered that one. And then obviously 7 then has to be the other one. So 7 is heptagon. For 9 sides, that one's somewhat easy to remember because 9 and nona are pretty close. And so for 9, nonagon is pretty close to a 9gon, so nonagon. For 10 sides, decagon, not really anything I can remember for that. And 12 sides, dodecagon. And really, for a lot of those kind of weird ones, we won't talk too much about them. So try your best to remember the names, but it's not super important. And then for inside, so if it's anything else like 11 or 13, we just call it an n-gon. So if it was 11 sides, it would just be an 11-gon, or 15 sides would be a 15-gon, and so on. So you just put the number and then put gon after it. Okay, so that's naming quadrilaterals, or naming figures and polygons, excuse me. Now, for regular polygons, in order for a polygon to be considered regular, it has to have all congruent sides and all congruent angles. So notice that the octagon that I've got for us over here on the right would be considered a regular polygon because all of the angles are the same and all the sides are the same as well. They're all congruent. So let's look at some examples and decide if these are regular as well. So for this first one, remember you have to have 2 things. You have to have all of the sides be congruent and all the angles be congruent as well. And it's actually labeled and all the sides are congruent. So we do have that first criteria being met. But let's take a look at the angles. And while it might look like some of the angles are congruent, the problem is you've got a couple of angles in the middle which are definitely bigger than some of the other angles. So all the angles are not congruent. The way we say not congruent is we put the congruent sign and then a slash through it. So no, this is not a regular polygon. All right, let's take a look at the next figure. So we've got a rectangle here. Let's see, is a rectangle regular? Well, are all of the sides congruent? And right away we can say no. As you're looking at the sides, obviously 2 of them are the same, but the other 2 are not. And no matter which 2 you pick, there's always going to be 2 more that are not congruent. So all of the sides are not congruent. So right away we can say that this is not a regular polygon. However, all of the angles are in fact congruent. So I mean, it was halfway there, but it has to be both. So this one is also going to be not a regular polygon. All right, let's check one last example here. So in this last example, let's first look at our sides. And if you look at all of our sides, they have those tick marks on them showing that they are in fact are congruent. So we meet that first criteria. Also, if you notice, all of the angles are also congruent. It's got them labeled for us, saying that they're congruent. So it meets both of those criteria. So this one actually is a regular polygon. In fact, this would be a regular hexagon. So it's got 6 sides. So we would say that n is 6, meaning that there are 6 sides. this would be a regular hexagon. All right. Some other things that we're going to be talking about as we study these regular polygons, and that's really what we're going to focus on for the rest of the notes today. When we talk about what's called the radius of a polygon, the radius of the polygon is the radius of the circle to each of the vertices of the polygon. In other words, if you were to draw a circle around this pentagon, and it wasn't perfect, but pretty close, then the radius would be the distance from the center out to the circle. In other words, it's really the distance from the center of the polygon to each of its what we call vertices, the vertex of the polygon. So any of those would be the same distance and would be called r. Now the central angle of the polygon is the angle whose vertex is in the center and sides are 2 consecutive radii, which is a lot of information, not something that probably makes sense right away. So let me do this to try to help us out. First, let's go ahead and redraw that circle around our polygon, and let's get rid of the r for radius. When we talk about the central angle of a polygon, what we're talking about is this angle right here. So if you were to draw in those lines that connect the center of the polygon to each of its vertices, then that angle right here would be considered the central angle of the polygon. Okay. Now, in order to find the measure of that central angle, we have a very nice, very helpful formula. The central angle is always going to be 360 divided by n, where n is the number of sides, and that should kind of make sense, because if you think about this as being a circle, so again, let me go ahead and draw in that circle one more time. So here that is for us. Then when you're looking at this, really, we have to remember that a circle is 360 degrees. So if we're taking 360 degrees, and notice that when we draw in those different radii, that you break it up into 1, 2, 3, 4, 5 sections, which also are the number of sides for our polygon. Then if we want to know what the measure of the central angle is, so if we want to know what the measure of one of these angles, then we just take 360 divided by the number of sides, which is 5, and 360 divided by 5 is 72 degrees. So then that would be the measure of our central angle. In fact, that's really useful because without even having a picture, we can go ahead and find the measure of a central angle for a number of different regular polygons. So let's go ahead and do that. Let's do some practice with it. We're going to do some practice with both classifying and finding the measure of our central angle. When we do central angle, I'm just going to call that CA. So as an abbreviation for central angle, I'm going to write CA in order to write that. All right, so let's just go through and let's classify each of these by its number of sides. So 3 is pretty easy. That's just a triangle. For 6, we just saw an example of this before. Remember, 6 is the one that has X in it, so this is hexagon, which means that 7, which is the next one, is going to be similar, but instead of an X, we put a PT, and that becomes a heptagon. For the other 4, these should be pretty easy. For 4, just be careful, make sure that you're saying quadrilateral and not saying square or rectangle or anything like that. But for 8, we probably remember this from stop signs and some other things as well. That would be an octagon. And finally, for 5, we can remember that as a pentagon. Okay, so now that we've gone through and classified, let's go ahead and find the central angle for each of these. So in order to find the central angle, what we're going to do is we're going to take the 360 degrees from our circle and divide it by the number of sides. So for a triangle, take 360 divided by 3 is 120 degrees. That would be the central angle for a triangle. Next, for a hexagon, if we take 360 degrees for our central angle, so let me go ahead and write that out. So central angle is equal to 360 degrees divided by the 6 sides, and 360 divided by 6 is 60, so that would be 60 degrees for our hexagon. For 7, we'll take 360 degrees and divide by 7. Now this one doesn't end up being a whole number, ends up being a decimal, so we'll go ahead and go to the nearest tenth, is going to end up being 51.4 degrees. For 5, we've actually already done 5. That was the example that we did at the very beginning when we were looking at central angles. So we already found that was 72 degrees. But I'll go ahead and write it one more time here. So central angle for a pentagon, you would take 360 divided by 5, and that's 72. We'll go a little bit out of order. Let's go ahead and do pentagon next, or octagon next. So octagon would be central angle is 360 divided by 8, and 360 divided by 8 is 45 degrees. Let's do one last problem. Let's do quadrilateral. So that would be 360 degrees divided by 4 for our central angle, and 360 divided by 4 is going to be 90 degrees. All right, so that takes care of the central angles as well as a little bit of classifying. We're going to spend most of the rest of these notes focused on how to find the area for a regular polygon. In order to do that, we need to talk about a special part of a regular polygon, which is what's called the apothem. So the apothem of a regular polygon is the segment from the center of the polygon, which is the perpendicular bisector to the side of the polygon. And that's a lot of information. So let's dive into kind of looking at what this looks like. So the apothem is a line segment going from the center down to the side of the polygon. And what it does is it splits it into 2 equal parts. And the perpendicular bisector part tells us that it also makes a right angle. So if we maybe called the center A and this point B, then we would say that the line segment AB is the apothem for this particular polygon. All right. So now let's go ahead and do some practice with labeling our figures. We're given some information about each of these regular polygons. We're told what the apothem is, what the side length is, and what the radius is, okay? So in each of these cases, let me go ahead and write that up here. We say that A stands for the apothem, that S stands for the side, and that R stands for the radius. Okay, so let's take a look at some examples of this. So on the first one, it tells us that our apothem is 6. So apothem I'm going to do in red. That's going to be this line segment from the center of our figure down to our side. So that would be a length of 6. And remember, that does make a right angle and splits this into 2 equal parts. For the side length, that is equal to 12 radical 3. For the side length, that is the length of any of the sides. Typically, we go ahead and label it as the same side that our apothem is going to. So that would be 12 square root of 3 right here. And then we usually do the same thing with our radius. We'll go ahead and draw in a line segment from our center of the circle, or center of the triangle, rather, to one of its vertices or one of its corners. And the length of that is going to be 12. Okay. Let's do the same thing with our regular polygon with 4 sides, which does in fact end up being a square. Let's start with our apothem, which is 4. So starting from the center of our square, if we were to draw a line straight down to one of the sides that splits both of the sides in half, then that's going to be our apothem, and it's going to have a length of 4. As for the side length, we're going to go ahead and label our side right here as being a length of 8. And then we'll go ahead and label our radius. So radius would be right here. And we know that it has a length of 4 square root of 2. All right. One last example, let's take a look at a hexagon. So for our hexagon, our apothem going from the center of that hexagon down to the center of, or the middle of one of our 2 sides is going to be a length of 4 square root of 3. Remember, that makes a right angle, splits your side into 2 equal parts, and here's that length. We're also told that the side length has a length of 8, and that the radius, so from the center to one of our corners, also has a length of 8. All right, so let's see how we can use some of that information in order to find the area of some regular polygons. So for the area of a regular polygon, what you're going to do is one of two things. The formula for the area of a regular polygon is 1/2 AP, where A stands for the apothem and P stands for perimeter. Or if you feel more comfortable doing it this way, you could take the area of one of the triangles multiplied by the number of triangles. So you could break your figure apart into multiple triangles. Personally, I prefer the first way using the formula, but some people might prefer the second way, and I'll probably show that for at least one of the examples. Probably the last example, I'll show you the other method, and if you wanted to go back and work it on the other ones, that would be okay too. Okay, so for the first one, let's go ahead and label what we've got for our information so far. So for our triangle, we're told that our apothem is equal to 7, so that would be this length right here. And then we're told that our side length is 14 square root of 3. Now, because this is a regular polygon, we also know that there are two other 14 square root of 3's, which we could label for our 3 sides. In other words, what we can do is we can either add together 14 square root of 3 times, or we can just take 14 square root of 3 and multiply by 3. So let's go ahead and find the perimeter. So the perimeter is going to be 3 multiplied by 14 square root of 3. And again, that's just because there are 3 sides to the triangle. So obviously, for the next one, for our square, our regular quadrilateral, there will be a 4 there instead. So let's see what that ends up being. 3 multiplied by 14 is 42. So the area for, or the perimeter for our triangle is 42 square root of 3. Now, in order to find the area for our polygon, remember that is equal to 1/2 multiplied by the apothem multiplied by its perimeter. So that's why we use capital P for perimeter. If we plug those values in, then we're going to take 1/2 multiplied by our apothem, which is 7, multiplied by our perimeter, which is 42 square root of 3. And when we simplify that, we're going to go ahead and multiply the 1/2, the 7, and the 42 together. So multiply everything that's not inside a square root together, and you're going to get 147. And then go ahead and just put the square root of 3 after it. Now, we weren't given any labels, so we won't worry about that. If you wanted to write units squared, you could, but you really don't need to. And then if you wanted to figure out what that was as a decimal to see about how much the area was, it ends up being about 254.6. All right, let's take a look at another example. So let's take a look at where we've got a square. So for our square, we've got our apothem, which it tells us is a length of 5. And then we've got our side length, which it tells us is a length of 10. Remember that since it's a regular polygon, then that means that all of its sides are 10. So then we could go ahead and find our area using that information. Let's go ahead and find our perimeter first. So our perimeter is that we've got 4 sides multiplied by the length of one side, which is 10, or just add 10 together 4 times, and our perimeter is going to be 40. So for the area, remember, we're going to take 1/2 multiplied by the apothem multiplied by its perimeter, which when we plug in those values, that's going to be 1/2 multiplied by the apothem, which is 5, multiplied by the perimeter, which is 40. And when we type that into a calculator to simplify, what we're going to find out is that the area for this for this square is going to be 100 units. Now, obviously for a square, probably the easier thing to have done would have just been to take side and square it, which would have been 10 squared, which also gives you 100. So it works out either way. Probably the second way, just doing it by side squared, would be better. In fact, going back and looking at our previous example, it would have been nice to have just been able to have used the formula for a triangle. Unfortunately, we didn't know what the height of the triangle was. That's why we would have some trouble trying to find it the normal way, rather than using this area for a regular polygon. Okay, let's take a look at two more examples of this. We're going to look at a hexagon and a pentagon. So let's go ahead and get these labeled. So for our hexagon, we're going to go ahead and label the apothem as being equal to 8 square root of 3. So that would be this distance right here. And then we're told a side has a length of 16. So that would make this 16 right here. Now remember, since this is a regular polygon, that all of the other sides are 16 as well. So to find the perimeter, you can either add 16 to itself 6 times, or remember, just take the number of sides multiplied by the length of the side, which is 6 multiplied by 16, and that's 96 for our perimeter. All right, so the area for this regular polygon, we're going to take 1/2 the apothem multiplied by its perimeter. So that is 1/2 multiplied by 8 square root of 3 multiplied by 96. So now to simplify that, let's go ahead and multiply some things together. Let's multiply together the 1/2, the 8, and the 96 first. That ends up being 384. And then all we have to do is write that square root of 3 after it. So again, multiply all the numbers that aren't under a square root together first, and then go ahead and put the square root sign after it. Now again, if you wanted to figure out what that was as a decimal, you could type that into a calculator. You'll find out that it ends up being about 665.1. And again, we don't have the units, so we aren't going to be able to label anything. All right. One last example we're going to look at is the pentagon. So we're going to go ahead and label this one like we've done before. So our apothem is going to be equal to 9. So that would be this distance right here. And our side length is going to be 13. In fact, that's the side length for all of our sides since this is a regular polygon. So let's first find the perimeter. You can either do that by adding 13 5 times, or remember doing 5 multiplied by 13. And that ends up being a perimeter of 65. So then what we'll do is we'll go ahead and plug that into our formula for our area. So 1/2 multiplied by the apothem multiplied by the perimeter. And then we'll plug in those two values. So our apothem is going to end up being 9. And our perimeter is going to end up being 65. This time you're good to just multiply all 3 of those numbers together. There's no square roots to worry about. And that ends up being 292.5. Now the other thing that you could have done, because remember that was just one way to work through each of these problems. Remember there was a second way. In fact, that's what I'm going to show you is this method right here, which is where you take the area of one triangle and multiply by the number of triangles. In fact, I'm going to do that for this last example just to show you guys one other way that you could work through these problems. What we're going to do is from the center of our polygon, we're going to make one triangle right here. And so what we're going to do then is we're going to find the area for this one triangle, which I'm going to go ahead and shade in now. So to find the area for that triangle, so the area, remember, is equal to 1/2 multiplied by the base, which is 13, multiplied by the height, which is 9. And when you multiply those together, you're going to get an area of 58.5. So then what we'll go ahead and do, since that's just the area for one triangle, is we need to figure out how many triangles would it take to fill up this pentagon. There's obviously one right there. Here is the second triangle. Here is a third triangle. Here is the fourth. And it looks like it would take a total of 5 triangles to fill up the pentagon. In other words, if we take that 58.5 and multiply it by 5, what you're going to end up with actually is going to be 292.5 as well. So notice that you get the same answer either way. It's just a matter of, would you rather find the area of the triangle first and then go ahead and multiply by the number of triangles, or would you rather just go ahead and find the perimeter and use the formula that we had for you? So it doesn't matter to me how you work those. It's kind of up to you. Obviously, both of those methods work anytime. It's just a matter of kind of working it however you feel more comfortable. That being said, guys, that wraps up Unit 6, so we will be preparing for the test very soon. It'll probably be sometime later this week. Until next time, have a good rest of your day.